Okay, I would like to cover one last topic here at the end of the PowerPoints. This is part 2 of our central limit theorem lectures here. And this is important because you'll see at the title here, Introduction to Hypothesis Testing. And hypothesis testing is really the bulk of what we do at the end of the course, and really one of the most powerful parts of statistics and inferential statistics, and we'll do a lot with hypothesis testing. So it's good to sort of connect with where we're headed. And this is the rare event rule for inferential statistics. So if under a given assumption, the probability of a particular observed event is very small, okay, and it might occur significantly less or greater than what we'd expect, we may conclude that the assumption that we originally make is not correct. One example I've given for this is we talked about tossing a coin, that if we flipped a coin 1,000 times and I got 994 heads, I think we all agree that would be extremely unusual. We really expect about 500 heads, 500 tails out of 1,000 tosses. And the assumption we would have to revisit is that the coin is a fair coin. We assume it's a fair coin. You would get 50-50 heads, tails, but 994 heads out of 1,000, I think we all think it's a rigged coin. We would revisit an original assumption that we made. So keep that in mind as we go through this little example. All right, so this is the body temperature example. So I think everyone's heard of that your sort of normal body temperature is 98.6 degrees, and we assume that the population standard deviation is 0.62 degrees Fahrenheit. So this is really your mu and sigma right there. Now, if you have a sample size of n equals 106, 106 people, find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. All right, now I'll show you this a little manually in a second, but we're going to assume that the body temperature has a mean of 98.6. Even though we don't know the distribution of the population, that sample size of 106 is definitely well above 30, so central limit theorem requirements are satisfied. And as you know, the mean of the sample means is the mean of the original distribution, that's 98.6. And the standard error of the mean is now sigma divided by square root of n. And notice for a sample size of 106, that new standard deviation, instead of 0.62, it's now 0.0602. It's really almost 1/100th of the original standard deviation. So this distribution of the sample mean much narrower around the mean than the original distribution. All right, that variation has been reduced by 1/100th roughly of its original value. So what we'd like to do, is sort of work through this manually, like we did the other problems. All right. So I'm going to draw with my pen here, and let's just assume. Okay. All right. This is the key thing. We assume that mean body temperature is 98.6 degrees Fahrenheit. Okay, and sigma is 0.62 degrees Fahrenheit, and they've given us a sample size of 106. So just remember, mean of the sample means is the mean of the original distribution, 98.6 degrees, and the standard error of the mean is sigma x bar, sigma divided by square root of n, which is now going to be 0.62 divided by square root of 106. All right, so we can draw a picture here very quickly. Again, my picture won't really do it justice, but this is going to be a very narrow distribution. Mu x bar is 98.6, and we want this probability that a mean temperature would be less than 98.2. So some tail over here. So we want the probability that x bar less than 98.2 degrees. All right, now if you look at our picture, our lower bound is minus 1e99, upper bound 98.2, and we'll put in our mu and sigma for normal CDF. All right, so this would be minus 1e99 98.2, and we'll assume the temperature is 98.6. And now again, we're not going to calculate. You saw that what that standard error of the mean value was a 0.0602, but again, we can just put it in directly, right? The 0.62 divided by the square root of 106. Sorry, I know it's a little hard to see the 1 there. So let me go to the TI. And why don't I just start over with normal CDF, since we have different values here. All right, so here we're going to need minus 1, right, exponent 99, and then this should be 98.2, and now our mu, we're assuming temperatures are 98.6, and sigma is, now I'll do 0.62 divided by, and we'll insert that square root of 106. So again, we can just put that in, that sigma x bar, directly into the TI. Don't worry about getting a decimal approximation. All right, and then we will paste, and you'll see this value. All right, 1.552 times 10 to the minus 11. So let me go back to my little whiteboard here. So this is 1.552 times 10 to the minus 11th. Now notice, right, this negative exponent means I would shift this decimal point 11 spaces over. I'd have to add 10 zeros. So notice, that is an extremely tiny probability. Okay, so the probability of getting a sample of 106 people with a temperature less than 98.2 is essentially 0. Extremely rare, extremely unusual. So what we want to look at here is there's really two possibilities. Either we got an unusual result from our sample. Do unusual and rare things happen sometimes? Sure. I mean, people win the Powerball lottery, win $500 million. I mean, very extremely rare things can happen. However, if we get a result like this, we may need to also question the assumptions that we went into the problem with. So let's go back to the PowerPoint and go through that. All right. One thing you're going to see, and I just want to connect this, we're going to see this later with hypothesis testing. If you calculated the z-score, notice that z-score is minus 6.64. If I asked you if a z-score minus 6.64 is extreme, we would agree absolutely. Remember, anything outside plus or minus 2 we consider unusual z-score. So once it's less than minus 2, it's unusual. This is a minus 6.64, which is much, much farther out on the z distribution to the negative axis. So that would be an extremely unusual z-score. And notice that tiny probability we got, right? The 1.55 times 10 to the minus 11th. There is a connection we'll see between that extremely tiny probability we got and this extreme z-score that we got. That's really the left tail area to the left of the z-score, right? But there is a connection there. The farther the z-score is away from 0, the smaller probabilities you're going to get. And again, we'll see that more with hypothesis testing later in the course. All right, so interpretation, all right? So, well, right, there's an extremely probability of getting a sample mean of 98.2 or lower when you have 106 subjects. All right, so at the University of Maryland, they did obtain actually this sample mean. That's what their results gave them. So, and after confirming that the data was sound, all right, two feasible explanations. One, the population mean really is 98.6, and this sample represents a chance event that is extremely rare. Or do we revisit the assumption that the population mean is actually lower than 98.6, and so that sample really isn't unusual, but the assumption of 98.6 is what the issue is here. And it says because the probability is low, it's more reasonable to conclude the population mean is lower than 98.6. All right, and maybe the true body mean body temperature is closer to 98.2. In other words, if we assume that mean body temperature is at a lower value, like 98.2, then that sample wouldn't seem so unusual or extreme. But we'll see a lot more of that later in the course.